So this meeting is being recorded as it says, and everything we're going to do from this point on is going to be recorded and is going to be posted back on YouTube. And hopefully those who are not with us will have a chance to go through it and discuss the things that are in there. And if they have any questions, they can always post them on the chat on Canvas. And it's a good idea to ask us questions in there so that we'll have a general discussion in there and so on and so forth, okay? So last time we were finishing chapter 6, and from chapter 6 after this thing in here, we're going to have an exam, okay? And the exam will be posted on Canvas, and you will have a little bit short time to go through it. I'm going to have actually from the previous chapter and this chapter, I'm going to post a quiz. So I'm hoping that you guys follow with the quiz on there too. I know a lot of people requested the passwords, at least for this session, and for some reason I don't see them all. And I think because probably they're using a broken link, they're using a link that is not working. Let me check quickly to see if there is any messages in here. Okay, let me answer these two people in here. I think I did answer them. Okay, let me answer these two people first before I start with you guys to make sure that they have the password. No, I did. Oh, I did. Okay, let me check the email because that's another way of getting these things in here too. Okay, I did answer. Yeah, check the announcements with the link. Let me answer this person quickly in here. She's asking basically because I removed the link from Canvas, and that's how it started somewhere else, where somebody shared the link with somebody else, and then people started coming in. Let me go quickly into the class so that at least. Copy the link. That's what I have been doing all day today, is that's basically answering requests. And I know I've been doing it on individual basis, but that's fine. Okay. Okay, I think I have everybody in here that at least answered everybody that I have in here, and I think everybody in here is legit, just to make sure. Okay, so last time we were finishing chapter 6, and chapter 6 is on Canvas. It's going to be on Canvas actually after we finish this session today, and the notes, at least the PDF version of the notes, and anything that I add will be there too. So hopefully you guys will have the video and also the PowerPoint. And if still you have questions, please do ask them, okay? So let me share the PowerPoint. So this is where we were last time. Is this thing not moving out of the way? Slideshow. Oh, current slide. Is this where we stopped last time? Yes.
I remember talking about those telescopes on the hills.
Was it here? No, we didn't get to this far. Basically adaptive optics and how that helps basically improve the resolution of the images. And I'm still cannot hear well, so on this thing in here. And I know somebody put something on the chat room in here. Yeah, okay, very good. So I think that's what it is. So right now we're going to move on past that topic to make sure that we finish as much as possible. So the ground-based telescopes, they're the ones that we've been talking about. This is in the visible region. I think also in the infrared region, that's what we talked about. We need to still talk about the radio frequency region, and then we also go into the higher frequency regions, and those we don't receive them on the ground, so we have to go to space and capture those frequencies. So one of the devices, one of the technologies that you guys that is used actually to persist the images is the CCD. That's what is it? The charged coupled devices. This is similar to what you guys have on your phones actually, or on the DSLR cameras that use the not the film cameras. I mean, the film is an old technology, but actually it worked for a long time. We still have a lot of records on film, and CCD actually uses electronics, and this is basically, it captures the different frequencies. So the frequency is imprinted, and also the intensity is printed. How many photons are captured also is imprinted, is recorded actually, and it's stored just like you store something on a hard drive, except that there is no hard drive in there, and the information can be replicated anytime. And it's actually much easier to analyze than with an optical. With something that you're looking at with the eye, or even something that analyzes the pictures. Once you have a data that is digital, it's much easier to be analyzed by a computer, and basically tells you all kinds of information on it and then replicates it. So the CCDs are actually, I mean, it's a technology that basically the way it works is that the details are imprinted on a very small area of the electronics, and the more data you store in there, the more capable basically the device is. That's what you hear on the megapixels and how many megapixels this camera versus the other one, namely how much storage can you put in a very small space. And mega is a million, so, and a pixel stands for what, picture per element, basically. That's what the pixel stands for. So this, how many basically details can you put in that space, and that is what the CCD technology is. So it's a brand new technology. It's modern basically, and it relies on I mean, it's microelectronics, and for us, all we care about is that, hey, you have an image. So when you take an image with your phone and you post it on YouTube later on, or sorry, on Facebook or something, you have a very sharp image. Okay. Okay. There is problem with when we're dealing with the infrared. In particular, the infrared is actually uses the longer wavelength than the visible light, and something that appears to us that it is completely opaque in the visible region is actually can have a lot of details in the infrared region. And you guys have heard of the goggles that the military used, and actually some of the people they use, hunters also use at night to look for animals, because again, it's sensitive to longer wavelength, and longer wavelength of the order of much higher than the micrometer, actually of the order of a millimeter to all the way to a few centimeters. And that is the region where the water actually starts to vibrate, and that is the principle behind the microwave actually region. And infrared is the how should I put it? Is a it's actually a topic in there too, for the telecommunications, for the remote controls and everything. There is a point I was trying to make in here and I forgot what it was. And yeah, infrared is associated with heat, because when that radiation hits our skin, basically our skin, we are mainly water. That's what we are. Humans are mainly big bucket of water walking with a little bit of non-water materials. And because of the fact that that region excites the water that is in us, we feel it as heat, because the molecules are agitated, and the more that they are agitated, the warm we feel. So what we normally associate with heat is actually what is in that region. So that's some of the phenomenon that is associated with the infrared. And before I get into this topic, I think this is I'm trying to go also a little bit expedited in here, moving faster. One of the things that we are interested in astronomy is using filters, trying to basically, let me see, I put stuff in here from things I have in here. These are some of the filters. If we were in class, I could have used them. So this is different frequencies filters. They basically will block any filter. We do them actually as part of the science experiments in here, where you use them trying to combine different colors, trying to filter certain colors. So filtering is an important aspect of things that we have to analyze. Once we receive a light, once we receive an electromagnetic wave, actually in general, we would want to see the different individual frequencies that are in there. One of the ways that we can do that, at least for the beam that we collect from a star is very far away from us. So the beam, as they arrive to us, they are all basically for more or less parallel. We need to focus them. And once they're focused, now they can run through a slit in here. A slit is an opening. And then you run them through to make them a little bit parallel so that you can run them through a prism, and then the prism will break them into different frequencies. Once you have them into different frequencies, different colors basically of the spectrum, then you can analyze them. You can imprint them, for example, on a CCD, and then from there you're going to analyze different frequencies. That do I have some missing frequencies or not, basically? And if I do, what happened to those frequencies? Probably they were absorbed somewhere in the midway. Maybe there is we want to know exactly the composition of different stars, what came. So a lot of information is just from the spectral analysis that you do in that. Similarly, then a prism, what you can do actually use, and I don't know, I think I did show you that the other day. There is the grating, which is a thousands of lines that are used. It uses similar technology, except it's a little bit more refined, because then you can have the individual frequencies. That grating can give you very, very fine detail exactly into the composition of the spectrum, what kind of frequencies you exactly have, because it narrows down on the specific frequency, and then it gives you exactly what kind of spectrum you actually have. And based on that, you're going to do an analysis and decide what is the structure of the object that emitted that light, and if there is anything that was absorbed, you can tell what's in between. And then depending on the shift, if the frequencies are shifted one way or the other, whether going to the low frequencies, that means the object is receding from us. If it moves toward the higher frequencies, that means the object is coming towards us. And we can actually determine its velocity. And that's how we do actually for binary stars, for example, if they're spinning against one another or something like that, just by analyzing their redshift or blue shift, and both of them, because at some point they're coming towards us and sometimes they're moving away from us, and based on that we can determine how fast they are moving. So there is a lot of information that you can determine. Unfortunately, you cannot do it for the sun, for example, or the star that is spinning around itself. I mean, theoretically, when the star is spinning around its axis, one side of it is coming towards us and the other side is going away from us. So there is a Doppler shift, but at this point you need extremely high sensitive device, extremely high precision, in order to determine that difference between these two frequencies. At this point, we don't have the technology for that. Otherwise, we can determine, for example, the rate at which a star spins, or at least the sun does. But at these extreme high precision devices, we don't have. But two stars spinning one against the other, that's actually something that is doable. There is an ongoing project, and actually I'm going to put a link to it, where some high school students actually, and college students, from high school all the way to graduate students, with their own, basically, with different backgrounds, where they can go and they teach them about this part of basically spectroscopy, and they learn about the techniques used. And then, because the universe, I mean, at least the sky, has millions and millions of stars, half of them are about binary stars. So what they do in this case, you designate a binary, and you decide, you know what, I want to study that binary. The reason being is because there is more stars than what we have astronomers. So astronomers are relying on basically average people. who are not even trained, like I said, even from high school, people who have no training whatsoever, all the way to advanced people who are graduate students in astronomy, working together and basically studying a binary and publishing the data on it based on basically, like I said, the rotation, based on how far it is, based on the period, based on their masses, all kinds of details is published later on, and you will have your name as part of the publication. So I post that link in there, and if you're interested, you can join the study, and you pick your team, and then you start working and have your name published in there. So that's a good thing to have. So I'm going to try to remember that, and hopefully post it. If I don't, please somebody remind me, and I'll post it for you guys. So if you're interested, you can do that. Anyway, it's not really hard. I mean, all you have to do is spend time first learning the techniques. Once you learn the techniques and your team basically designates a binary, they send the request, I think, to the observatory in Australia, and Australia will basically spend a few days collecting the data for you guys. And then after the data is collected, they send it back to you, to your team. And now your team spends a lot of time basically going through that data and analyzing it. And at the end, you publish something, which is a big achievement. Okay. And you help in the process also learning more about stars in the sky. Okay. So radio astronomy is a different thing altogether. First of all, the antennas are much bigger than because the wavelengths are much longer. Now you're dealing with meters. You see here the person standing in here. This is one of the early. Actually, the first radio telescope that was built by, used by Jansky. So again, it was really discovered by accident, if you wish, in the 1930s. He built this telescope and he noticed that the same frequency came the day after 4 minutes later, and then the day after 4 minutes later. So he immediately thought that and suspected that this is related to objects that are far away, that they are not in that they are not on Earth, because this has to do with the spin of the Earth around its axis. Remember, the sidereal day is off by 4 minutes compared to the solar day, basically 24 hours. So he immediately thought that this must be coming from deep sky, and then later on, basically, radio astronomy was born. Initially, it was not taken seriously, but later on, there's a lot of information that can be learned from radio astronomy, especially from very far galaxies that have their frequency shifted all the way to the radio region, and they emit extremely powerful signals that tell us a lot of details about those faraway objects. So it's really an amazing topic too. And they require big antennas, basically. You cannot operate with small antennas. However, you can have your own. You can build your own. This is actually from eBay. I did not buy them. I was planning actually on doing this summer project, working on them. This is the RTL SDR chip, which is a dongle which goes on your computer. It has a software, it has everything. And then if you notice on the side of it, on this side in here, that's where the antenna is hooked. Actually, you hook up the antenna in here, and the antenna can go from few centimeters all the way to several centimeters, basically, when you extend and open it completely. And actually, it can give you some decent frequencies. However, you have to be very careful, because you're going to pick up a lot of basically noise that is coming from transmission on Earth. So you have to really make sure that you're actually getting an object from the outside of the Earth in order to study it. And usually they are very far away objects to give you those long wavelength, the radio waves. You can do this. This thing costs $25. The dongle itself, and the antenna is about $15. So this is a cheap thing that you can start your amateur radio astronomy with it. So this is a fun thing. I was planning on doing this in the summer, but now with everything is going around, I don't know what. Probably I still do it, because the antenna can be indoors. So this is not you don't have to be outside and worry about contact or anything like that. So this is something that you can do at home. And again, there are all kinds of other dongles out there, but I like this one. The RTL SDR has a lot of good reviews on it, so you can use it and connect it to your computer, and the software basically is self-explanatory. All you have to do is follow the instructions in there, and you start detecting signal. And after it detects the signal, make sure it's a signal that is not from Earth. Basically, one of the telltales is signs is for it to, if it's periodic and it comes, if it's not periodic, then most likely it's coming from Earth. If it's periodic, then you have to monitor what's its period. Then it has to do with the rotation of the Earth, or is it something else? Okay. So that's basically, it's not like a broadcasting station that is somewhere in Germany and you're picking it up. Okay? So make sure you do that. Okay. So it's fun if you want to be busy and do something in the summer also in the same time. Okay. These are some of the, the screen is in the way. I'm trying to, okay, never mind then. Okay, here it is. So again, these are some of the very long wavelength radio telescopes out there. Some of them from the 400 meters all the way to the 22.8 meters. And I think this one is an airborne, isn't it? Anyway, they're very long wavelength, basically, like I said, and there is more and more interest in radio astronomy. And radio astronomy is a very powerful technique to discover all kinds of details about our galaxies, basically, things that you cannot see with the visible eye, with the naked eye. And then one of the properties of also waves in general is that the longer the wavelength, the further it's going to go before it starts to decrease. I mean, that's why it's used actually as a radio in radio telecommunications. The voice that we hear on a regular basis is actually can go from few hertz all the way to 20,000 hertz. And that is actually, yes, it's a short wavelength, but it is not in the radio region. So that's the ones that we hear. But again, the sound that we hear is actually not electromagnetic in nature at all. It's just basically mechanical. It's the vibration in the air. So what we do in this case in here is you have a device on your phone that captures your voice and converts it into a signal, electronic signal. And that signal is still of that same frequency, which is kind of something that we hear. So what you do in this case, you take that signal, the one that you're talking with, and then you bundle it together. You put it with a radio wave. The radio waves are very long wavelengths that can go around buildings, basically, and transmit over very long distances. So you take that, you combine the two waves. This is called the load. And you take it with the carrier, and the carrier in this case is actually that very long wavelength, and you transmit it. Once it's received by my phone, once you are on the other end, now you're receiving it actually a very long wavelength. So your device first separate the two. So there is a separation first of the two frequencies. The carrier is thrown away, it's useless. And now the load, the actual message, is amplified first because it comes super weak. And then the speaker plays it back on your ear. So that's how the radio itself, and actually TV also, and all of the devices work. So we cannot hear long wavelength. And for example, in the savannah in Africa, and also even under the oceans, whales and elephants, they communicate for very long wavelength, and we cannot hear them. We cannot hear them because they're communicating with very long wavelength. Some of the wavelengths we can hear, but sometimes they communicate and we cannot hear it because super long wavelengths, because our ears were not equipped to that. So that's basically one of the things that you have to know about long wavelengths. Have you guys seen the movie? What is that movie? Finding Nemo? Anybody?
I love that movie.
You know what, that she was talking to the whale and she was talking in a very long wavelength. That's what I meant with it. Okay. Yeah, it's the point in here is the frequencies. I mean, bats apparently they have a very much wider range of frequencies they can hear. We are limited in terms of that. They can hear much lower frequencies. I mean, very high tone, I mean, very low tone, and very high tone also frequencies, things that are outside of our range. Same thing also goes with dogs too, and all kinds of animals, they have different frequencies. The point I'm trying to say in here, radio astronomy, really we cannot hear it. you have to convert it to something that we can hear. We have to have super wide, basically, ears in order to capture probably that, just like the elephant does. Okay. And for the whales, I really don't know. I don't know much about biology, honestly. But for whales, probably they hear from their skin or something like that. But they capture those sounds too, at least for them under the oceans. And the advantage of that is, for them, they can communicate over very, very long distances. An elephant can send a signal, and another elephant several miles away can hear it, because again, it's very long wavelength and it travels longer distance before it dies, versus a short wavelength. Short wavelength travels, it carries with it more energy, but it doesn't go very far. So that's the difference with it, of the two. You have to have a very, very powerful source to push it very far away. And that's what you actually hear also if you go on radio stations, doesn't matter which, they will tell you we are broadcasting with so many megawatts, because megawatt is 1,000,000 watts, and the watt is actually the power, how much energy is transmitted every second, to try to cover as big of an area as possible. But yet, if you move, for example, from Riverside area, and if somebody is broadcasting in the FM region, frequency modulated region, you cannot capture it probably far away from here. And AM, which is amplitude modulation, that actually can be captured a little further away, but it's still, the frequency will die and the signal will drop. And that's actually what's going on actually with your phone. Right now I have 2 bars because I am a certain distance away from probably the closest transmission. And if I get from it, I'll get a higher and higher bars. At some point, if I move away and away, the signal drops and I don't have anything at all. So by the time I'm receiving it, by the time my phone receives that signal, it has to actually amplify it first for me to hear it. Before that, it throws away the carrier, which is the one that we're talking about in here, is several hundred meters. 400 meters is a lot. It's half a kilometer almost. Okay, and this is a big telescopes in here. Okay, so this is one of the images that is captured, for example, for a galaxy, and you will see the jets of the streams in here. Again, it's the radio frequency we can see, but it's transmitted, it's basically converted via software, depending on their frequencies and depending on the intensity, into different colors so that we can visualize it, because we are visual creatures. We understand better if we see something than if we hear about it or something like that. For some reason, I only have 12 people attending, and I think they're still having difficulty with this. Out of this classroom, it's about a quarter of everybody who's supposed to be in this class, and that's probably we'll see what kind of problems they run into, and hopefully we'll fix that. Okay. So this is the telescope that is in West Virginia that we're running. That's 100 meters. That's again radio telescopes. This is the Atacama. This was a successful project that you have basically how much, like 30 miles or so, something like that, is spanned with telescopes. And in this case, what it uses a different technology in here. It's not a single antenna, but rather it's several antennas working together in tandem. So basically what you do in this case is one antenna, at least for radio signal, will capture a signal. Now, if you adjust it right, the next one can capture the other part of the wave. This is half a wave, the other one half a wave, and now all of a sudden you have captured as if you have a bigger antenna. It acts as a big antenna. So radio waves, you can do that for it, and you can have a very wide region in here that you can capture still using a smaller antenna, but you have several of them working together using the so-called interferometer technology. Basically, as long as you have to do them right, you have to adjust the distance between them correctly. And if they're in a separate, different time zones, you have to really, and they can work in different time zones, you have to adjust them correctly, and now it's computer aided so that you can do that. And in doing so, you actually can capture much, much longer wavelength, and also capture because again, the signal is super weak, even though they're supposed to travel the longest. You can amplify it as much as possible by capturing more and more frequencies. In other words, trying to increase the resolution of these devices. Okay, trying to have a better image using radio telescopes of the source and trying to pinpoint where the source is coming from. That's another problem also, because the resolution also means, okay, I have two potential sources. One is this way and one is that way, and anywhere in between it could be. If I can narrow that region, I have a much better, basically, reception than if I keep it very wide and very spread. Again, this is the very long baseline array. Look at the spread for this one. This is for the United States that's managed. All of these antennas are acting just like one, basically. They are working together just like one telescope. And this is another dish telescope. This is probably the largest one in the world at this point. This is about 300 meters, 1,000 feet is about 300 meters in diameter. That is a big telescope. Again, this is basically, it's made on the ground itself. It's a valley between the mountains that basically they converted into a telescope. All the beams that come from the cosmos, they come and hit it, and they are all reflected to this point in here. It's like the LMB of a regular TV antenna, basically. And that is the signal that is carried in there and later on analyzed and studied and all of that in the computer room. The problem with this antenna is you cannot reorient it. You cannot say, for example, today I'm studying this star, this star. Tomorrow I'm going to move it this way, and you can't. So what you do in this case, you play with the receiver in here and try to capture different angles. So this is not really a. I mean, it's very useful in terms of capturing at least the region of the sky, but you can't really move it to different sides of the sky. Hopefully, the Earth itself rotates enough to give you more and more regions. This is an observatory because of the fact that there is a problem with the ground, basically, reception. Because again, the moisture in the air really creates interference in the wave and make the image blurry. So you'd want to go as far as you can away from it, and this is even going a few 1,000 meters, basically, a few kilometers in the sky. You can get a much better image, and you eliminate as much as possible the interference that you're going to see. Okay, again, this entire chapter is about telescopes, so hopefully you guys are having at least, if you're considering getting a telescope, which is a good thing to do, but this is actually a much higher end telescopes. Again, in the visible region, this is the space-based telescopes. Now, once we go into higher frequencies, then at least in the visible, we have the ground-based telescopes that help us. But again, they suffer from the problems in a sense that you have the atmosphere and you have all kinds of things. And we said we go up in the mountains, away from the light in the deserts, and hopefully we can use them. And we saw a lot of examples of that. But if you take it above the atmosphere, if you go to space, then a lot of these problems are eliminated. One of the other problems that is eliminated actually is the heating of the telescope, because you would want to keep it cool. And that's actually one of the problems that the infrared telescopes suffer from, because the heat itself is actually infrared too. And you're trying to capture an infrared signal, and the device becomes warm enough so that itself is going to emit. So you have to eliminate that. So what you do in this case, you cool it. You put it in a cooling system. But if you are in the ground and trying to cool it, the problem with something that is cold, and you can pull it from a refrigerator and see what that is, the condensation starts to happen on it from the warm atmosphere around it, because of the water that is in the moisture that is in the air. So now you have a problem, because then the whole device becomes useless, because it's really not good. But if you go above the atmosphere, then the reception will be, you avoid that problem because there is no air to worry about. You can cool it so the device does not interfere with its own self in terms of the infrared, but then you have now a much better reception. So in the visible region in here, and here it tells you the range of that device. So visible region, you have, of course, the Hubble telescope, and it's been in operation since the 1990, and we got a lot of results from it. One of its problems early on when it was launched is that immediately after, in order to save money, basically, they didn't test the optical the optical part of the telescope, which is the biggest part, and the first images came blurry, which was really a big problem. So what they had to do to it, they had to do what we do normally to our eyes. Basically, they put the lens in front of it to refocus the beams, and that fixed it. It took about 3 years later on. It was really something that that was bad. I mean, that you after you finish your project and at the end the images were not sharp. But then after that, the Hubble telescope operated immaculate, and then it exceeded its own life basically when for how long it's supposed to live. And we got amazing pictures of our own solar system and also our galaxy, and even further away, far away galaxies. One of its projects is the Deep Space project, which looked at different regions of the sky for galaxies as a few percentage, basically immediately after the universe were born. So this was one of the major successes that we had. And then we have the Chandra X-ray telescope. That's for X-ray region. Again, that gave us a lot of images of the some of the most powerful, basically, sources of radiation in the universe. And there is also the Newton, which is in since 1999. The gamma ray. There is the Spitzer telescope, which is in the infrared. There is another one, which is the which one is the gamma ray that I'm. Gamma rays is a big challenge trying to study it, and actually because of the fact that it's extremely energetic and it penetrates anything. So you really have to use it some sort of in direct approach to trying to study it. Basically, the effect of a gamma ray is that, for example, for the cosmic radiations, is once the gamma ray hits in, it's going to accelerate particles. So what you're doing, you're actually studying the particles and deducing backward, basically, the source of the gamma ray and where it came from. So gamma radiation is kind of very powerful in here. The Spitzer telescope in here, and look at its size, it's 0.85 meters. It's less than a meter because, again, it's an infrared. So this is also this is actually a very powerful telescope because now it's above the atmosphere, so we don't have a lot of the problems that we have them underground. We got a lot of amazing also studies with this devices, because one of the things that we did, actually, we mapped the entire universe and we got the feel for it on how it looked immediately through studying basically the microwave basically region of the sky, and having a mapping of how the universe was immediately after it was born, after 300,000 years after it was born, 400,000 years, because that's when the first radiation started to come. And of course it's shifted in the red region, so we have to go into that region to study it. So the Kepler project also was an amazing, this is in the visible light, that's actually the one that allowed us to study exoplanets, planets outside of our own solar system. So we have had theory before based on our own solar system that planets first must exist around other stars, number one. Number two, also, they must exhibit the same behavior or similar behavior to what the planets do on Earth, namely, around the sun. Namely, that there is a region of planets that are rocky planets, and then there is a region where there is a gas giants, and probably also the other. So we had that theory based on what we have seen on around us in here in the solar system, but we never really had a confirmation until this project in here. Actually, there was some early indications of existing of planets. Basically, one of the early indications was the Doppler effect that some of the stars exhibited, because you see them basically oscillate around their position, and the only explanation for it is that there is an invisible object around them with which they oscillate. And that was one of the early technologies used in there. And actually, some of the technology used also for determining Kepler planets, but those are supermassive planets, because you have to have a planet that can impact its own star. For that, it has to be a huge planet. But then the technology was refined and other methods were discovered, and now we have exoplanets, planets outside of the solar system in the thousands, basically. So we know what we suspected before, now we know for a fact. So this is some of the projects that are out there using different telescopes. So we are not wasting our time, basically, studying our own solar system, because hopefully if we can then find another star, then we have some understanding of how that star would host a different planet similar to ours. Okay. This is some of the pictures of basically nebula and different galaxies and different, using just this Spitzer telescope, which is in the infrared region. And again, it gives you the source of heat where the stars are forming. We cannot see them with our own eyes, or even with the Hubble telescope, because Hubble telescope operates in the visible region. But with Spitzer, you can see them, and you can have a much better picture in there of what's going on. This is before light is coming from them. So these are the hot regions in the sky. So that's basically some of the powerful stuff that we can collect from these objects. Now, the ultra deep field, this is basically a small region, a narrow region of space where you can look at this. These are galaxies, they are not stars. Okay, and some of them are, of course, they're redshifted because they're moving away from us. And the further they move, the faster they move, the redder they appear. So, and this is from the early universe, basically. Some of this probably are stars too. The Chandra X-ray powerful, satellite was used mainly for the powerful sources of X-ray radiation. Okay, so that's really the centers of galaxies where black holes are and things like that. But you can have X-ray radiation even from our neighbor, for example, star, which is Proxima Centauri, because it's a dwarf star. Basically, it's a small star, and it emits just in the red region. But sometimes, because it does not have a lot of gravity to hold its radiation, sometimes it emits X-ray radiation, and that's why some astronomers believe that the planets next to it, although there are so many Earth-like planets, they cannot support life just because of this fact that every few years, basically, you have so much powerful, although short-lived X-ray radiation that is coming from the star that can decimate any life around it. And that's basically some of the things that we can discover with these things. Now, in the future, this is some of the stuff that we're looking at in the future. And this is the James Webb Space Telescope. It was planned initially to be launched in 2018, but I think now it's delayed until April of next year. Hopefully, with this stuff that is going around the world, it's not going to be too much of a problem, because what should I say? Because things are being delayed at this point. It uses a similar technology like when we talked about, I think, let me try to escape this in here. It uses similar technology like the telescope that we talked about. It's so many mirrors, basically, one next to another, and they basically combined into a big mirror. So it's going to solve that problem of basically the telescope under a lot of pressure. So you can still use them, and they become very powerful telescopes, basically. And you fix some of the mechanical problems you have them with the other telescopes. So again, this is proposed to be launched in 2021, basically next year, and hopefully that's going to be in space there. Okay. I wanted to have this one as a super fast thing in here. Okay. And this is the extremely large telescope also that is in ground that is going to be launched. This is some of the future stuff that is going to happen. Because I want to dedicate some of this presentation today to remember the project that we guys were supposed to be working on. I'm going to stop the sharing of the screen in here. We're done with the PowerPoint, so I'm going to post it on Canvas. And we want to focus now on the project itself. So let me pull the stuff from the project. But let me check also if somebody is trying to log in and they cannot. Oh man, some people are still asking for the passwords. Let me share the password with some of the other people. At least hopefully if they join, they can join somewhere in the middle, better than nothing. Oh, I'm sorry, Brittany. I don't know. think let me also send an email. I think I disconnected her because I didn't know who she was, so I removed her from the session, and that's my fault. Okay. Okay, so we'll have to fix that. And okay, so we were supposed to have that discussion. Anyway, this whole thing is recorded, so we're going to have it on YouTube, and I will try to communicate with her to see how we fix that. And there was another 2 other people actually asking for the password, so I just sent it to them. And let me go into the sharing of the screen for any questions? No? Okay. That's not the file. So like I said, I wanted to, that's what we discussed last time also we need to do, and that is to have a little bit of time dedicated to the retrograde motion, and that is this project that you guys are looking at. Yes?
I can see
Is
it.
this what we said we should do?
Yes.
Okay, very good. So basically with this project, look at the data in here. This is giving you different, the day in here, the right ascension for the, this is for Mars, and the declination for Mars, okay, on that day. The next day, 7/20, which is, this is July 10th, this is July 20th, August 1st, and if you follow this line in here, you're increasing every few days in here, almost 10 days, different observations of the planets, basically Mars. Following now we are in June, November 2005, the 10th. Now we move on to this table. We're November 2005, December. Now we're in January of 2006. So we have the data in spans of 10 days or so observations for planet Mars, okay? So what I'm gonna do in here, I'm gonna go back into the table here, the graph here, and put those dates in here, basically. Let's go back into the first one in here. So I'm doing this. On July 5th, the right ascension is 1 hour, 13 minutes. And the declination is, remember, this is a measurement of an angle, the right ascension, okay? So remember, that's 24 hours, basically, around the Earth. So that's basically what that is. So it's an angle, really. It's not a time. It's not like 1 o'clock in the morning and 13 seconds, 13 minutes or something. So, and here it's 4 degrees and 54 ascension, 54 minutes. The declination is how far it is from the, basically the ground. Okay, so from the horizon, basically. So I'm going to look for 1 hour and 13 minutes. Again, in here, 13 minutes. If I look how many divisions in here, I have 1, 2, 3, 4, 5, 6. So there is 60 seconds in a minute, I mean in an hour. So 60 minutes in an hour. So this is 10 minutes. This is 20 minutes. This is 30 minutes, 40 minutes, 50 minutes, and 60 minutes plus 1 hour. It becomes 2 hours, okay? The second hour, and so on and so forth. Here, 2 hours and 10 minutes, 2 hours and 20 minutes, 2 hours and 30 minutes, 2 hours and 40 minutes, 2 hours and 50 minutes. And then when you add 60 minutes to an hour, it's going to be another hour, so it's going to be 3 hours and so forth, as long as we know what that is. Now, the declination is actually going from 0 degrees all the way to 25 degrees. Now, let's look at the table in here to see where we put this point. I'm going to put a tool in here to see how I'm going to do it in this thing. So I'm going to put my comments in here. For you, you don't need to do what I'm going to do now, okay? So, but you can basically use whatever pen and marker you have, that will be fine. So we know the declination is 1 hour and 13 minutes, and the right ascension is 1 hour 13 minutes, and declination is 4 degrees and 54 seconds. So here is 1 hour and 10. So 13 minutes is somewhere almost halfway, but to this side of the 20 minutes, okay? And then it's 4 degrees and 54 seconds. 4 degrees and 54 seconds is almost 5 degrees. So this is the point where I'm going to put it, somewhere in here. Okay? Now, this is the first point of data that I have it in here. The second one is 1 hour and 37 minutes, and it's 7 degrees and 9 seconds. So I need to find 1 hour and 37 minutes. So this is 1 hour, 20 and 30. 37 is closer actually to 40 minutes. Okay? And I'm supposed to go all the way to 7 minutes and 9 seconds. 7 minutes and 9 seconds is slightly above 7 minutes. So again, this is 4. This is almost, actually, it needs to be closer in here because 54 seconds is very close from 5 minutes. So this is 5, this is 6, this is 7. Remember, 20, 30, 37 is somewhere in here. So this is about the 7 minutes. So let me pull that tool again. So the second point should be somewhere in here, 6 and 7. So it should be somewhere in here. Okay, they're not exactly the same point, but hopefully you see the thing in here. If I'm doing it with your pen on a piece of paper, that's how I'm going to do it basically. But I'm using this tool in here, which is kind of the comment tool from Adobe. You don't have to do it with this tool in here. I'm just basically trying to show you guys how to use it in here. The background stars are these stars actually on those dates, and you can look at the catalog in there on those dates and find exactly what those stars are. And they don't change much. So these are persistent stars, so you can find on those dates what they would be, what constellation is that, and you can find them. But I think you don't have to. I already told you guys you skip that part. On the next date, it's 2 hours and 4 minutes, which is 4 minutes is just between 0 and 10 minutes. I mean, a little closer to the 0 minutes than the 10 minutes, but halfway somewhere. And it's 9 minutes, 9 degrees and 36 seconds. 9 degrees and 36 seconds. So it's 2 hours and somewhere in here. And it's 9 degrees, and so this is 7, 8, 9 degrees, and how much? 9 degrees and 36 seconds, which is slightly more than halfway. Because remember, 30 minutes, 30 seconds is is 1 degree. 30 minutes is 1 degree. So basically, what is it? 30 minutes is 1 degree, okay? So here are the minutes, the seconds are a degree, and 60 degrees, 60 minutes are a degree. So basically a little over half. So I'm here a little less than half on the hour thing, and I'm going to go in here. What was the first number? I forgot it. 9 degrees. So I'm gonna go 9 degrees. So this is 7, 8, 9. So it's somewhere in here. Okay, do you guys see the pattern now? So you're going to continue following this line and connecting these points, okay? Because at this point, at some point, I need to connect these points in here. So this point connects to that point, connect to that point, and I need to find where the next point is. At some point, what I will see is that this planet starts to move back and go forward. When it moves back, that is when the retrograde starts. At some point, it asks you a question in here. So the ecliptic is basically where the apparent stars or apparent objects move in. What are the meaning of the term retrograde motion and prograde motion? Retrograde is basically when it's moving back. Prograde is when it's moving in the same direction. What about Mars begins retrograde motion? You can actually see it visually from here, okay? At some point, it's moving back. Right now it's 3 degrees, so it's actually for 3 hours and 54, 3 hours. At some point it should be moving back, okay? So we're moving up, 3 hours and 13 minutes, 3 hours and 22 minutes, 3 hours, 26 minutes, and now we're moving back. So we should expect the retrograde around this time, but you have to plot it to make sure it is, okay? So around that date, you say, okay, this is when the retrograde motion starts. You guys understand how we're proceeding, or should I explain it further? At least for this part.
I understand.
Okay.
Sir, it's good? Good or more?
So for that part on the actual worksheet that we have to fill out, is that the points that we're plotting?
I'm sorry, can you repeat that, because kind of I did not hear, because again I'm having problem with my sound. Actually, it's not your problem again. It's the. Can you repeat the question?
So for the project, are we actually going to have to use these points to plot
Yes.
the actual worksheet?
Yes, you're going to do the actual points in here. You're going to go back to this data. Okay.
Ooh.
Okay. Point by point. Okay. You have to go follow point by point. You're going to go. I just drew 3 points for you guys. You can do the rest of them. I just drew these 3 points in here on the chart. And if you have problems with it, please let me know. Okay. I don't want it to really be too much of an issue in here. I want you guys to really be how should I put it? Enjoying it, in other words, because it looks too much. But once you start doing it, and it should make you feel good, because then you're doing something that you know how it's working. Because now the 2 hours and 22 minutes, if I want to locate this point in here, it's this point in here basically. On the chart, it's 2 hours and 22 minutes. So I know this is 2 hours, this is 10 minutes, this is 20 minutes, 22 minutes. I can use actually a ruler if I'm doing it with my at home. So let me pull another thing in here that I know works at least on this software. So this is 22 minutes. Of course, don't draw lines with. So this is roughly 22 minutes. Okay. Now I need to find the second point on the chart in here that tells me to find 11 degrees and 12 minutes. 11 degrees and 12 arc minutes should be, this is 10, 11, and 12. 12 is about a quarter. I mean, is it, no, sixth of the way, okay? So sixth of the way, again, should be, so this is 11 and a sixth of the way, okay? Roughly, so this is the points basically. So if I'm going to draw the points in here, this is how I'm going to find the next point in here. Oops. So that's where the 2 points in here meet. Okay. Now I want to find the next point on the graph. It doesn't matter. Now let me pick another point at random, and that's going to be. Let me pick this point in here and see where I can find it. Okay. 3 hours and 22. Of course, you're going to do all of them. Okay. So 3 hours and 26 minutes. 3 hours and 26 minutes. So this is 3 hours, 3 hours here. I'm sorry, 10, 20 seconds, 22, 26. 26 is almost halfway. So this is 20, this is 30. It's actually, I can find it with a ruler. I can find exactly where the point is. So I can draw this line as far as I can, okay? Because I don't know where the other point is. So the other point says, it's 16 degrees and 26 minutes, arc minutes. 16 is here. This is 15, this is 16, and followed by 26. 26 is slightly half than midway. So this is 16, half, Control Z, half than midway, should be somewhere in here. Almost where that star is. Where these two meet are here. These 2 points, they meet here. That is the point we're looking for. And then, of course, I have to keep track of these dates, because these dates are in linear increments of 10 days each, and draw them and follow this graph. This is probably the most difficult part of this project. Once you have it done, then you can answer the rest of the questions. Okay? Does everybody understand how this is working, at least for drawing the graph?
Yes.
Okay, very good. If you have difficulty, please do not hesitate. Don't leave it up to yourself later on, and then you start struggling with it and you have a problem with it, and that's not good, okay? So in here, there are two models. Basically, it tells you in here there is a geocentric model, which is, and then it asks for the epicenter, the epicycle, and the different, which you can find from the literature just by reading up there. You can find them. If not, you can Google actually. And if you still have questions, please do ask me. And according to these models in here, this is where the Earth is. And I'm going to take a ruler now and draw a line from the Earth to 1. This is where the star, where Mars appears, at least in the sky to us on that day. If I take it again from here, and okay, I cannot start it from there. Run a line from Earth. This is how it's going to appear on that day. And there's a limitation on this tool in here. So the third one, I cannot draw because the minute I think I draw in there, it's going to tell me to remove that line. So I'm going to draw the third point. Of course, you're going to leave that second point in here. I'm going to also remove the first one. So we're going to draw several lines in here, going through this one. This is the third one, because I cannot draw from using this tool at least points in here that are on the same origin, because it thinks that it wants me to remove that one. So I'm going to draw another one in here that goes from 3 to 4, from the Earth to 4. And I draw these points in here and I label them. This is point 1, this is point 2, this is point 3, and so on and so forth. I should have labeled them while we were doing that. So this would be point 2, okay, in here, and how it appears in the sky. And now we're going to go to 5, which is just barely above 4. 4 was here, 5 was here. 6 now starts to move back. 6 now is back. Remember, 5 was up in there. So from here, the planet Mars appears to be moving backward. Okay, 7 is actually further down. 7, it looks like it's moving in the opposite direction where everything else is moving. And 8 actually starts to now move forward again. Okay, 8 is actually higher than 7, and now the planet appears to be moving in the forward direction. So again, what you're supposed to do in this part in here is draw these lines and label them 1, 2, 3, 4, 5, 6, 7, 11. Okay, all the way to 11. And the bottom in here part of the instructions, this is the sun is in the Earth. You are, the sun is the center. You are on the Earth, and you're looking at different, looking, for example, at Mars, and Mars is here. So as far as you're concerned right now, it appears in the sky to be in this point in the sky. So let's make that point. So this is where Mars looks like, at least on this sky. Here. Okay. And later on, when both Earth and Mars move around the sun, this is where actually it looks like. It is. So do you see that? It moved forward in the sky, just like everybody else. So let me remove this one because I can. Oh, actually, this one I can probably. Yeah. We could have left the first one in here because the other one you cannot draw a line. So this is where Mars appeared the first time around. I'm going to label this one 1, this one 2. And now from when the Earth is moving, it has moved forward. So we're going to take a ruler actually for this part and actually do it. How we're doing on time? Still good. So this is the third. Now the fifth point again. You see here, they look like they're the planet has moved back apparently, and that is because the Earth is actually catching up with Mars. And now it's moving actually back further than the second point in here. It appears to be moving back. This is 7. Now it appears to be moving forward. Remember, 6 was here. Now 7 is in the same direction as everybody else. So the planet now appears to be, now if I do 8, this is here. Actually 9, it has moved the furthest point still in the sky. You guys understand how this is, at least constructing how this is, you're going to construct it? Actually, I did it basically for you guys in here, but you understand the idea for it, that the planet appears to be moving back and then moving forward. Models do that if the Earth is the center of the solar system and if the sun is the solar system. But one of them is real and one of them is actually mathematically correct, but it's wrong in terms of the actual situation. Yes? Which one is correct, guys, do you think? Which one is the real thing?
sun centered one of them.
Yeah.
The sun is the center of the solar system. But both of them give you the same, basically more or less the same thing. And you can label this one from 1 to 11, and these things need to be labeled from 1 to 9. I know the instructions is saying from 1 to 10 or from 1 to 11, but actually it should say only from 1 to 11, from 1 to 9, okay? What is it? The second correct model, we know how that's true. So this part is wrong, okay? So you need to fix this one. Position 1 to 9, not position 1 to 11. Okay? The first one was correct from 1 to 11. But the second one, I think Andrea is the one who pinpointed that to me, because when I did this one the first time around, I was just cut and paste basically. But this is not correct, okay? This is 1 to 9. Do you guys understand the difference? This is 11 points in the sky, 11 positions in the sky for Mars. This is actually only 9 of them, as you can clearly see from 1 to 9. Of that, you should be able to understand that part. This is basically a distinction between the inner planets and the outer planets versus the Earth, okay? This is the point of opposition. And there is the inferior conjunction. Hear it a lot, and you will see it a lot in the literature in there, okay? Again, at some point, Mercury, not Mercury, and also Venus appear to be doing a retrograde motion just because of the fact that they are catching up with the Earth. It's the opposite story than the Earth and Mars. Now, this calculation in here, this calculation is critical. I think it's the last part of the project. What you're supposed to do in here is, if you take Mercury in here, it does 2.89, almost 3 months around the sun. That's its period, how long it takes for it to go around the sun. 3 months, almost 3 months. 2.89 is slightly less than 3 months around the sun. But in our months days, basically it's 60 days plus almost 90% of a day, which is 90% of a month, which is what, 9 times 3 is almost 27 days or something like that plus. So that's its period in months. The period of Venus is 7 months and almost and a half, slightly more than half. Earth is 12 months. Mars is 22.6 months, almost 2 years. Ceres is 55 months. It's almost, what, 6 years. Jupiter is almost 12 years. And Saturn is another one of them. From there, you're going to calculate this expression. So what you do in this case, you take 2.89 times 12. Let me show you the calculation quickly in here. Let me share with you another screen in here so that you guys see the math behind it. It should not be that hard. But let me create this thing in here. So let me stop sharing that screen and share with you this calculation here quickly. If you have difficulty with the math, please let me know. I really don't want you to struggle with this one too. I don't want you to really have an understanding of how that works. That's all. I don't care really honestly about the math part of it. But if you have difficulty with it, I would like to have to move on with that. Okay, so I'm going to share this part in here. So you guys are looking at my notepad in here. So we're doing Mercury right now. We're looking at the data. So Mercury, it has 2.89 times 12. That's the Earth divided by. I have to open parentheses. I cannot just do that. Now, what that bar means, what this thing in here in math means, if you guys have seen it, what these two pipes mean, they mean absolute value. That means we don't care which one you subtract from which. So if you tell me I want to subtract 2.89, subtract from it 12, you're going to find a negative number, but at the end, you're going to make it positive. So what you do in this case, actually, you do 12 minus 8.9. So in other words, you're going to get a positive value. Somebody is asking a question here. You don't need to edit a PDF, okay? You're not going to do it on PDF. You're going to do it actually on your own. You have to do the whole thing by hand, okay? Somebody is asking, Andrew is asking, if it's possible for us to edit the PDF. You cannot edit PDF. We can change it into a fillable format, but then you can only fill some fields in it. So you'll have to be, for the drawings, you cannot. You have to do them by hand. So basically what you do in this case, you print the thing. Is the library open for you guys or not? I want to know.
No.
Nothing is open? we need this to be somehow printed, because if you can't print, then what you got to do is try to do it with Paint. Microsoft Paint, if you have Paint or any painting software in there, you can draw with that one. It's easy, okay? Or at the end of the day, what you can do, actually, you can draw it on a piece of paper and scan it, or take a picture of it with your phone or something and send it to me. I need to have you guys have a feel of how this thing works. This is, again, you only learn by doing. You don't learn by just watching people do. That's really how the rule is. So in this case, we're still doing Mercury. So what I'm trying to say in here, it doesn't matter if this number turns out to be positive or negative. You're going to put just the positive part of it there. That's it. So again, I'm going to go into my calculator and find what that number is. So I'm going to find 2.89. Let me first of all stop sharing the screen to show you exactly how the calculator have a feel for it, so that you enter the numbers. I'm going to share this screen in here. You're looking at my calculator right now, which is a Microsoft Mathematics, which is a free software you can have on your computer. So 2.89 times is the point in there, 12 divided by, open parentheses, 2.89 minus 12, and close the parentheses. And if I hit enter, it gave me a negative number. I don't care for the negative part. All I care about is 3.80, which is roughly 3.81, okay? So I come back into this table in here, and I put 3.81. Do you guys see that? I already did that for you guys. So it's 3.81. Then how long after this date, 3 months later on, in 0.81, I'm going to find this date in here. So the next occurrence will be 3 months from February, January, February, March, April, May, okay? And 0.829 months, what is it, 0.81? Let me look at this number again, and 0.81. So basically, 0.806. Okay, let me do the math in here so that you guys see that. 3 months from February is March, April, May. So we know it's going to be in May, sometime in May. What date of May it's going to be? It's going to be 81% of a month. 81% of a month is 0.81 times 30 days. So 24 days and a third. So I'm going to count it just as 24 days. So today's date, or at least when it occurred last, according to the table, is February 26. Let me bring it back to you guys so that stop sharing this thing in here. And go back to the PDF file where we were before. So we want to go 3 months from February 26 and 24 days. 3 months is going to be February, March, April, May 26 is 3 months. Don't worry about that month with 31 days and a month with 28 days. So March 26, you're going to just get a rough ball, plus 24 days. 27, 28, 29, 30, 31. Now I have the subtracted 8 days from 24. 8 days from 24, again, I do the math, do 24 minus 8. With the calculator, 16 days. So it's going to be the 16th of June. So that's my answer in here, 16th of June of 2020. Do you guys see? I want you guys to follow this example roughly so that you have an understanding of how you're going to do the rest of the calculations. If you have difficulty, please let me know. So again, I'm going to go back in here and share again the screen. What is it? This PDF. So this number gave me about 3.81. Okay, I know it's 3 months and 81% of a month. So it turns out to be 3 months plus 81% of a, which is 0.81 times 30 days. So it's going to be 3 months and 24 days, basically. So when I calculated it, I found 3 months from 2/26. That's the last occurrence of 2020. So if I add to it 3 months, that should put me and 5/26, 2020. Add to it the remaining 24 days, it put me in June, which is 16, 2020. So my prediction for the next time when Mercury goes in retrograde motion is going to be June 16, 2020. Okay? Ignore this number is turned out to be a negative number, negative 3.806 or something. I round it and I made it roughly to be 381. It doesn't matter. Even the 24 was not exactly 24, 24.3 or something like that. A third of a day doesn't mean much, so we're talking about dates in here. So we came with an estimate of June 16, 2020. Okay, do you guys have an understanding of this one works? If not, please come back to this part of the video and watch it again and make sure you understand it. And if you still are struggling with it with your specific data, please let me know, or talk to Andrea, send her a message and have a discussion with her or me, doesn't matter, and let's get this thing done. Does this sound like it's a good plan?
Yes.
Okay. So I want this to be done, please. This is the last part in here of the reports, and you will hopefully will have an understanding and appreciation of these things in terms of the motion of planets around the sun. You guys want me to put this text file for you guys as an example of calculations?
Yeah.
Yes, please.
Yes.
I'll see you guys next week, okay?
Mm-hmm.
Hi.
See you next.
Okay.
Thank you.
Please ask questions on the forum, okay? Don't leave it without any questions in there, okay? Thank you.
Thank you.
Thank you.